G'day everyone. Today we are going to study some more organic chemistry. So we're going to start off by looking at aldehydes and ketones. And we can create aldehydes by oxidizing primary alcohols, and we can create ketones by oxidizing secondary alcohols. And let's talk about what that means. So you can see here on our chart, we have an alcohol. If the OH group is on an end carbon, we call it a primary alcohol. When we oxidize a primary alcohol, we end up with an aldehyde. Now, if the OH group is on a carbon other than an end carbon, we make a ketone. We call those types of alcohols secondary alcohols. So when we oxidize a secondary alcohol, the C double bond O or carbonyl group ends up on a carbon that is not on the end. So those are named differently, and they're classified in a separate family called ketones, although the properties are quite similar. So there's a carbonyl group. You can see we can have variable R's in two different locations there. And if neither of those R groups are hydrogens, then it's going to be a ketone. So if either of them is a hydrogen, then it's an aldehyde, which means simply it's at the end of the chain. So here's an example of an alcohol, a primary alcohol. We have an OH group on an end carbon. And if we oxidize it using an oxidizing agent like dichromate ion and sulfuric acid, then you can oxidize this alcohol to an aldehyde. So this is in fact what happens inside your liver when you consume ethanol in beer, wine, or spirits. You have an enzyme in your liver that breaks down alcohol into an aldehyde. It also leaves a rather nasty taste in your mouth the next day. If you consume too much alcohol, you'll notice a distinct taste in your mouth. That's an aldehyde. Now, the aldehyde actually gets further broken down by another enzyme into carbon dioxide and water eventually. And some people genetically lack this enzyme. And as a result, they are allergic to alcohol. When they consume alcohol, even in small quantities, they end up with a red face and they feel terrible. And it's because they lack the enzyme that breaks down ethanol in the liver. And it accumulates and it has a toxic effect, making you feel sick. So obviously people that are allergic to alcohol do not consume it because it makes them feel so ill. There's also a medication that people can take if they are alcoholics that causes the accumulation of aldehydes in the liver and make you feel sick when you consume alcohol. It's called antabuse. So that's one treatment for people that are alcoholic and have a problem consuming too much alcohol. And it's hoped when they are on antabuse that they will be deterred from drinking alcohol. So the naming convention for aldehydes, the two carbons, so it's F, and notice the end of the word, if it's a C double bond O carbonyl group on the end carbon, it's an aldehyde. So the name ends in AL. The oxygen came from the oxidizing agent, the dichromate ion. And here we have an alcohol that is on a carbon that's not on the end. It's a secondary alcohol, and when we oxidize it, we end up with a ketone. So the name of a ketone, in this case, we don't have to state where it is because there's only one location that can't be an end carbon on a 3-carbon structure. We call this propanone. So it's not until you get 5 carbons on a chain where you have to start identifying where the ketone is, where the double bond O is. Again, the oxygen came from the oxidizing agent. So I've gone over naming aldehydes again. We simply put AL on the end of the word, drop the E. Here's an example here of methanol. And here's another example here of a butanol. So it's 4 carbons. So we have a butanol. In this case, we have a chlorine group on the 3rd carbon. So we call it 3-chlorobutanol. And again, we're only going to require you to know the systematic names. You can see the carboning chain numbering always starts with the functional group. The C double bond O is going to be the 1st carbon in the chain. So Now, ketones, of course, occur when the C double bond O is not on an N carbon. When you oxidize a secondary alcohol like 2-propanol, the 2 indicates the OH group is on the second carbon. And when we oxidize it, in this case, we end up with a ketone propanone. So when we name ketones, we simply drop the ending of the name, the E in the end of the name, like butane, and we change it to butanone. Butanone would be a 4-carbon ketone. In this case, we have propanone. No need to use a number because there's only one location. In this case, we have a pentanone. Now you can either have the double bond O on the second carbon or the third carbon. So you have to distinguish between which carbon has the functional group on it. So we use the number. In this case, it's the third carbon, and we use a numbering system that's going to use the smallest possible number. The common name of this would be diethyl ketone, but the systematic name, which is the one we want you to use, is 3-pentanone. And in this example on the far right here, we have a 2-carbon chain. So it's an ethanone, and we have a phenyl group or a benzene ring attached to the end carbon. So we call it the 1-phenyl ethanone. This is carbon 1 because that's where the functional group is. This is carbon 2. Hence the name 1-phenyl ethanone. We could have a 2-phenyl ethanone with the phenyl group attached to the other carbon. So you can see again, the numbering of the chain here uses a numbering system where you get the lowest number possible. So ketones are used in the production of resins, antiseptics, and insecticides. And they are very, very popular organic solvents in the manufacture of many petrochemicals. Now we're going to talk about carboxylic acids. A carboxylic acid has a C double bond O and an OH group on it. So if we oxidize a primary alcohol or aldehyde, we can produce acids. So I'm going to show you where this is in our chart. The chart, here's our alcohol. When we oxidize it, we get an aldehyde. If we oxidize it further, we're going to get an acid. So we're going to look at that step now. So this is the oxidation of ethanol, a 2-carbon aldehyde, and we oxidize it using dichromate and 10% sulfuric acid. And notice that an oxygen from the oxidizing agent ends up on the carbon chain, making now an acid. So we would call this ethanoic acid for 2 carbons, and we change the end of the word. Now, this particular acid is produced in some cases from the oxidation of alcohols in wine, and it can cause a kind of a vinegary flavor, of course, in the wine, which can be used in cooking, but it's certainly, most people would reject drinking the wine and instead use it for cooking purposes if it starts tasting like vinegar. And that's because you have allowed bacteria to get into your wine while it's fermenting, and the bacteria has started oxidizing the alcohol into acid. Now, when we name carboxylic acids, you simply drop the E, like butane, drop the E in butane, and you're going to replace it with oic acid. So a 4-carbon carboxylic acid from butane would be called butanoic acid. And here are some more examples. In this case, this is, we've already talked about, it's a 2-carbon organic acid. We notice C double bond OH. It's always at the end of a chain. Can't be on the middle of a chain because it requires 3 bonds. So it's always at the end of a chain. That's going to be called ethanoic acid. And we're always going to start the numbering from the functional group, the acid group. In this case, we call this benzoic acid is the common name, but the systematic name would be a 1-carbon acid with a side chain that's a phenyl. So we call it a methanoic acid, and the side chain is phenyl methanoic acid, is another name for benzoic acid. And some more examples here. You can see we have a 4-carbon chain here. So it's going to be called a butanoic acid. And on the 3rd carbon, we have a chlorine group. So it's 3-chlorobutanoic acid. In the second example, we have again, we have a C double bond OOH. You can sometimes written like this instead of written like that. And we're going to call this a 3-methyl benzoic acid. And if we look at this example down here, we can see it's a 5-carbon, a 4-carbon, so it's going to be a butanoic acid, and we have a side chain on carbon 1, 2, 3 on carbon 3, so it's 3-methyl butanoic acid. Another example here, carbon 1, 2, 3, 4, 5, it's a pentanoic acid, and it's going to have a methyl group. There's 4 methyl groups on here, so it's a tetramethyl. So we identify the carbons where the methyl groups are, 2, 2, 3, 4, tetramethyl pentanoic acid for 5 carbons in the chain. Another example here is an acid, an organic acid, but it's got an acid at each end. The common name for this is a Dybbuk acid. It's used in the manufacture of nylon. We're going to call it a dioic acid. Since it's got 6 carbons, it's a hexane dioic acid. And again, it has to be on an end carbon because it requires 3 bonds. So the only place we could put them would be on the ends. And this is used to make a very common nylon that's used in all the airbags in cars are made from nylon 6,6, and the 6,6 in the name comes from a 6-carbon carboxylic acid, a dicarboxylic acid, and the other compound they use to make the nylon 6,6 is a 6-carbon diamine. So if you put an amine group at each end, you get 1,6-diaminohexane. That is the second substance that they use to make nylon 6,6. They make a long polymer by reacting the acids at each end with amines at each end of the other substance used to make nylon 6,6. So they call that hexamethylene diamine is the common name for it, and a Dybbuk acid and hexamethylene diamine make nylon 6,6 here in Kingston. So next reaction we're going to talk about are making esters. Esters are popular flavoring agents in many foods. So we can see that if we take an acid and we react it with an alcohol, we end up with an ester. So to show you this, here we have an acid. It's a C-double-bond-OOH. It's ethanoic acid, 2 carbons. And we're going to react it with a 1-carbon alcohol. In this case, it's called methanol. And we end up, when we react those two together, you end up with an ester. And the ester would be called methyl ethanoate. The OL changes to YL. The alcohol name always comes first, and the acid name always follows. And the end of the name changes to O8, which we'll talk about in more detail in the next slide. So we call that methyl ethanoate, a simple ester made from methanol and ethanoic acid. And of course, water is released. It's a dehydration process. The OH always comes from the acid, and the hydrogen always comes from the alcohol. Now, we're going to look at another formation. Here we have ethanol. It's a 2-carbon chain with an OH group, and we have a 2-carbon chain with an acid at the end. We call that ethanoic acid. So we get ethyl ethanoate is the resultant ester made from the release of water. Use heat and a source of acid to actually accomplish this. Used to perform esterifications in the high school lab when I taught in high school. A number of them are very pleasant smelling. So the first part of the name always comes from the alcohol, and the second part of the name always comes from the acid. So if I was going to draw here the structural diagram for 2-chlorobutyl 3,3-dimethyl pentanoate, I'm going to show you the alcohol it came from and the acid it came from. The alcohol name always ends at the YL, which is why I have it written here in red letters so you can see it. So the alcohol it comes from is a 2-chlorobutyl, which means it's a 4-carbon alcohol. And we are going to place, in this case, the OH on the end carbon, and then the carboxylic acid is at the end on the pentanoate, which is the 5-carbon. And we can see there's 2 side chains on the acid part of the molecule on the 3rd carbon. So This is the first carbon because it's where the acid group is. We could show the elimination of water. And now what I forgot to do up here was indicate the presence of where the alcohol group is. The alcohol group is on the first carbon, so we're going to indicate it by saying butan-1-ol or 1-butanol. You could put the 1 in either location. So again, note that it should have been changed up here as well. So that should have said 2-chloro-butan-1-ol or 2-chloro-1-butyl to indicate where the OH group is, because the OH group could have been on the second carbon, either this one or this one. So the acid here is 3,3-dimethyl pentanoic acid. As I mentioned, those are where the side chains are, the methyl groups, and it's 5 carbons with a carboxylic acid on the end. So when we combine these two, we eliminate water and you get your ester. When you're looking at an ester, you can always identify the acid from the carbon that's double bonded to the oxygen. So once you see a carbon double bonded to an oxygen, that's the start of the acid. So we go 1, 2, 3, 4, 5 carbons. So that's a pentanoic acid. And 1, 2, 3, we have a methyl group, 3,3-dimethyl pentanoic acid. We look at the alcohol group. It's a 1, 1, 2, 3, it's a 1-butanol. And we have a 2-chloro-1-butanol is the name of the alcohol that it came from. So properties of esters, again, like we said, they come from acids that typically have very pungent odors, but as soon as you take an acid and react it with an alcohol, you end up with a very pleasant smell. Banana flavoring can be made, peppermint flavoring, a whole host of tastes and flavoring agents can be generated from combining carboxylic acids with alcohols. In fact, aspartame is an esterified version of a dipeptide, which is 2 amino acids linked together, and then it's esterified, and that's where aspartame comes from, a sweetening agent used in soft drinks. Now, let's talk about how we could make an ester from ethane. So what we're going to do first is start with ethane, and we are going to, in this case, remove some hydrogens and make ethene. Then we are going to add water to it and make an alcohol. From the alcohol, we're going to oxidize it to an aldehyde, oxidize it further to an acid, and then recombine it with the alcohol to make an ester. So those are the steps involved, and I'm going to show them over here. So we start with ethane. We take the hydrogens off, we make ethene. We add water to it and make an alcohol, ethanol. We use a oxidizing agent like dichromate, sodium or potassium dichromate, and sulfuric acid, and we make ethanol. We oxidize it further into ethanoic acid, and then we combine it with the alcohol that was previously made, ethanol, and we get ethyl ethanoate. Again, the double bond O shows us where the acid part is. It's a 2-carbon acid. The O shows us, the single bond O shows us the alcohol. In this case, it was ethanol. So to put all the names up, ethane changed to ethene, to ethanol, to ethanal, to ethanoic acid. And then we take the ethanol that we made and combine it with the acid, ethanoic acid, and we made the ester ethyl ethanoate. Another functional group we're going to talk about that's very commonly used in organic chemistry are called amines. Of course, amines are found in amino acids, which are the building blocks of all proteins. All amino acids have on one carbon, the N carbon is a carboxylic acid, and the next carbon has an amine group attached to it. And there are 20 different derivatives of that structure that goes into all the proteins found in life forms. Now, so the amines, we're going to talk about how we could make an amine today. We can make an amine from a substituted alkane, like a chloroethane or a chloromethane. And we could then substitute the NH3 for a chlorine and end up with an amine. So we're going to look at that a little bit more closely. Before we do, we're going to talk about how we can classify amines by the number of hydrogens on it. If we have one functional group attached to an amine, we call it a primary amine. If we have two functional groups attached to the nitrogen, in this case, two methyl groups here, there's one methyl group there, we call that, and when there's two, we call it a secondary amine. And when there's three R groups attached, we call, instead of hydrogen, we call it a tertiary amine. So now we start with, in this case, with chloroethane, and we combine it with ammonia, NH3. And when we combine ammonia with NH3 with the chloroethane, what happens is you're going to remove the HCl as hydrogen chloride, and you're going to make an aminoethane. That's the simplest way to make an amine. Now, when we name amines, there's a couple of different methods we use. In this case, we have a primary amine. We call it simply aminoethane, an amino group on a 2-carbon chain. And there's aminoethane. Now we can have a secondary amine. In this case, we call it methylaminomethane. It's a 1-carbon chain, and we have a methyl attached to our amine, so we call it methylamino methane, 1-carbon chain. Not really a chain, is it? And we have a tertiary amine here. And when we have a tertiary amine, again, we can see it's a 2-carbon chain. So we call it an ethane. And now we call it a dimethylamino ethane. So here's our ethane, and this is a methyl and a methyl. So it's dimethylamino ethane is the systematic way of naming it. And that's how we prefer you to name these compounds. Now, amines are frequently used in the manufacture of disinfectants and insecticides, herbicides, dyes, drugs, fungicides, soaps, cosmetics. A whole range of products use amines. And amines are quite smelly. So it's recommended whenever you're using amines that you use a fume hood. Now, the last functional group we're going to talk about are the amides. So the amides are replacing the OH group on an acid with an amine group. So we take a C double bond OH and replace the OH group with an amine, NH2. So we now call that compound, where you have a functional group, a C double bond O NH2, we now call that an amide. And they're named as amides. Rather simply put, if it's a 2-carbon, instead of calling it ethane, you call it ethane amide. If this is 1 carbon, it's called methane amide, is the system we use to name amides. So again, here's our acid. We are going to add ammonia or NH2 group to it, and we end up with an amide, a C double bond O NH. And of course, we can have other groups beside hydrogen attached to that nitrogen. And we'll talk about how we accommodate that in a name. So they're named similar to aldehydes. Again, I said you just drop the E in the name and replace it with amide. And if it's nitrogen that's being, if you replace something on the nitrogen atom, you use the prefix N to indicate the presence of that group attached to the amide. So we'll show you some examples of that. Here's an example here again of a simple amide. It's called, well, we don't know what it would be called because we don't know those R groups are variable. But if the R group is attached to a nitrogen, we use N in the name, which I'll show you. So we're always going to release water when we perform this reaction. So propanamide would be 3 carbons. Again, the N carbon is C double bond O NH2. 2-butanamide tells us it's a 4-carbon chain with a double bond between the 2nd and 3rd carbon, and the N carbon is, again, C double bond O NH2. So here it is, C double bond O NH2, 4-carbon chain attached to the 2nd carbon is a double bond. That's where the 2-butan comes from. And we can add side chains as well. In this case, we have a pentyne amide, which indicates there's a triple bond Between the second and third carbons, it's a 5-carbon amide. So here we go, 1, 2, 3, 4, 5 would be the numbers of the carbons. The numbers are determined by the presence of the amide group on the end carbon. And you can see there's the second carbon triple bonded to the third carbon, which is what the 2 tells us. And on the fourth carbon, this is the fourth carbon, there is a methyl group attached where the 4-methyl comes from. Now we're going to show you what we mean by placing functional groups on the nitrogen atom. In this case, we have a 6-carbon amide, so we're going to have a C double bond O, NH2, except on the hydrogens, on the nitrogen, we have 2 carbon groups. There's one ethyl group, there's the other ethyl group. So because these ethyl groups are on the nitrogen atoms, we indicate N, N dash diethyl, and then the hexanamide comes from 6 carbons in the parent chain, 1, 2, 3, 4, 5, 6. So that's how we accommodate the names with functional groups attached to the nitrogens. So we're going to name this one. Here's a C double bond O, NH with a methyl group attached to a nitrogen. So it's N-methyl, and it's only 1 carbon, so it's a methane amide. Now, how do we know this is a double bond O here? Well, we know because carbon forms 4 covalent bonds. So if there's a single bond on either location, we need 2 more bonds to make that carbon stable. So that's why we know that this has to be a C double bond O. And again, in this case, we have we can call this, it's simply a 2-carbon amide, so it's going to be ethane amide. In this example here, we have methyl groups attached to nitrogen again. This is a C double bond O, and we're going to use N in the name. There's 2 methyl groups, so it's N dimethyl. And on the second carbon of our propanamide chain, we're going to have a double bond, and that's where the 2-propan comes into play. So let's show how we could make an amide from ethene. So we start with ethene. We're going to add water and make an alcohol. Then we're going to oxidize it to an aldehyde. Then we're going to oxidize it further to an acid. Then we're going to add an amine by adding another chemical compound that's got NH2 attached to it, and we make our amide. So to show you, we start with ethene by using 10% sulfuric acid. We go to ethanol when we add water, and then we're going to use a oxidizing agent like potassium dichromate and 10% sulfuric acid. We make ethanol, oxidize it further to ethanoic acid, and then we're going to add, in this case, aminomethane, and we add aminomethane to it, and now we have it completed. So we now have our amide, C double bond O, NH2, except this is going to be N-methyl ethanamide. So putting the names up here, N-methyl ethanamide. Again, because there is a methyl group attached to this nitrogen, we indicate it by using N as our symbol before methyl. And it's 2 carbons in our amide. That's where the ethane comes from. All right, so we've come to the end here. So I just want to summarize all the organic reactions we've looked at, and I want to remind you that you will be allowed to use this particular printout sheet that's finished for the exam. We talked about how we could take an alkyne and add hydrogen to it to make an alkene, add more hydrogen to make an alkane. Then, of course, we can take our alkene and halogenate it with chlorine or bromine or iodine to make halogenated alkanes. We can add water to an alkene and make an alcohol. We can then, this is really coming from the alkene, this arrow. And again, it's just showing it in a different location because we're going to use that halogenated alkane in other reactions in a second. Okay, we can go between alcohols and halogenated alkanes. And we can take our alcohols and dehydrate it using sulfuric acid and make ethers. And then we can dehydrate our alcohols to alkenes. We can oxidize our alcohols from a primary alcohol, you're going to get an aldehyde. From a secondary alcohol, you're going to get a ketone. Remember, it depends where the OH group is. If it's on an N carbon, you end up with an aldehyde. If it's not an N carbon, you end up with a ketone. Then we can take our aldehyde and oxidize our aldehyde to a carboxylic acid. And we can then add an alcohol to it and have an ester. And you can add water to our ester and change it back into the acid and the alcohol that produce the ester. We can add ammonia to a halogenated alkane, and you end up with an amine. And then we can take an NH2 group attached to a carbon and add it to a carboxylic acid, and you end up with an amide. And that ends our organic chemistry. So good luck. This is the last lecture. So get ready for the exam by working hard, and we'll sign out now. Take care, everyone. Best of luck on the exam.